Welcome back, students. We have been discussing diffraction. We said diffraction is bending of light. That's one definition of it. Because when you have an aperture or an obstacle, when you send light through the aperture or when you block it with the obstacle, then light seems to bend around the edges. If it is an obstacle, then it bends inwards, and if it is an opening, it's an aperture, then it flares out. We said this is because of the wave nature of light, and we explained that too. And we said the final definition of diffraction would be: diffraction is interference of many waves. So that would be a better definition of diffraction. So when millions of waves, thousands, lakhs and millions of waves come and combine and they superpose, then you get the diffraction pattern. So even if you have a single slit, then this is what you will get. The diffraction pattern is what you will get. It will look like the light flares out from the slit. Even if you send a parallel wavefront, then the parallel wavefront does not go parallelly from that point forward, but it seems to flare out. It seems to widen through that slit. And we talked about central maximum. That's where like you have the most important part of diffraction pattern is the central maximum. And then you'll have other maximas, and between them you'll have minimas. Minimas are points where you get no light at all. It's the point where you get darkness is called as the minima. So if you were to draw this, just to recapitulate what we have done so far, it's like this. So if I send light, suppose that this is an opening, a small slit, an aperture, then I have a screen here. Then if we send parallel wavefronts through this, then after this slit they don't travel parallelly, and they seem to, if they travel parallelly, what do you expect to happen? This is what you should get. Okay? So the light should have gone like this. So whatever light comes in, it should go parallelly and then hit the screen. So we would have expected to see brightness only in this, and that is what your ray optics predicts too. But that is not what is happening here. So what is happening is a flaring up of light. Okay, so there is a point where you get a minimum, right? So this is P. So this is minimum. And at the same distance here, I'll call this as P dash, you will get another minimum. So these two are called as minima. So and you get to see light up till here. So there is, the brightness is not limited to this area. This also gets bright and this also gets bright because light seems to kind of flare out. Okay, so this is what is called as diffraction, the bending of light around sharp edges of apertures and obstacles. So this is, see, I want you to understand that this is not a regular spreading of light. So what I mean by that is, suppose I have a point source here. And then if I have an opening here, and then if I keep a screen there, ray optics tells you that you are going to have light up to here, right? So this is your bright area. So this is what the ray optics says. You may think that like it is wider. No, this is not what we are talking about. This light still travels in a straight line. Notice here, still travels in a straight line, but it's just that the angle is, it maintains an angle because of this. Because this is not a a plane wave. If it were a plane wave, then I would expect the brightness only to be here. But this is not a plane wave. You know, it's going to be a spherical wave now. It's going to be a spherical wave. Since it's a spherical wave, and after this it extends, and I expect it to be bright over this point. Okay, this is what I expect it to do. But what actually happens is that it's not bright only here, it's bright here too. So the light seems to bend now. So this is also bright and this is also bright. So I want you to understand this. Just because I have drawn this straight line doesn't mean that it is a case like this. It is not a case like that. It should have been like this. This black is equal to this blue. Similar case. It's the same case. But when I expect the light to be confined to this length or area, however you want to call that, it is not confined there. It seems to bend further and then makes the dark places bright too. This is what we call as diffraction. It's the apparent bending of light, and this happens because of the wave nature of light. I want you to understand this. And again, so this is going to be bright. I'm going to use a different color now. So this is what we call as the central maximum. It's going to be very bright, and this point is minimum, so dark. So you have maximum brightness here, and you see then the brightness goes down, and this is where you get the first minimum. And after this, again, you will have something like this. But then these would not be so intense as this one is. These spots would not be as bright as the central spot is. So you would actually see this. You would see something like this. Okay, this is very bright thing, and then after this you will see something like this, something like this. But this will be really bright, and these two will not be that bright. So this is what you will be seeing here. Okay. Imagine right here, right here. So this corresponds to this, and this corresponds to this. This corresponds. This is what you will see. So I have drawn it like this. The maximum tells you that you have maximum brightness here at the very center of this. So this is about basically diffraction. But in this case, I've got a slit. Okay, I've just got a slit. One small, like the slit is going to be something like this. Okay, so it's a small slit. This opening. If I have a sheet like this, and this is the opening. That's a slit. So for that slit, you get this. Okay, and what did we say? We also said something else. We said that if this is sufficiently large, like if it's far off, then if for the point P, like all these points, like it will go parallel to that. If it's so far off, all of these will meet there. Okay. But this picture is not very correct because I will take a short distance anyway. But you can see that. So then we said that if this is theta or this is theta, this will also be theta, and if A is the width and this is a path difference, right? So this was, suppose lambda is the path difference between the first and then the last, then you know that A sin theta is equal to lambda. You know that A sin theta is equal to lambda. So sin theta is equal to lambda by A. And for small angles, because it's going to be very small, the flaring up is not too wide. It's going to be very small flare up. Bend very slightly. Will not go exactly parallel as you've got here, but there will be a slight bend. And the bend would become very apparent when you go longer and longer distances. Reasonable distances, the bend is not much. Okay. The angle clearly. So then I can say that theta is very small. So sin theta will become theta and divided lambda by A. Okay. So this is what theta will be in radians. So we did this for this. So it's for a slit. Well, what if you have a circular aperture? Instead of a slit like this, I'm going to have a circular aperture. So this is the sheet. Instead of a slit in the sheet, I'm going to have a circular aperture. Now I'm going to send light through that aperture. Okay, so this is the sheet, and this circular aperture through which I send the light. Then what do you expect to happen? On the wall, on the other side of the wall, I'll probably expect to happen, see something like this, right? Okay. This should become slightly bigger, yeah, on the wall, and then you'll see the the diffraction pattern. But you see after that what happens? Then you get after the first bright, and then this darkness, and then the next one, right? So you see after this, you will see things like this. But then as you go further away from here, then the intensity will be reduced, and after like 1 or 2 you wouldn't even be seeing it. Okay, but this is what you will be seeing for the most part. And so this is bright dot, bright dot, bright dot, bright dot. You will see circles like this. If you send light through this, this is what I will see on the screen. But as we saw here, the brightness will reduce and then after some time totally vanish in a sense that you will not be able to perceive those things. So, but this is the pattern you will see if you are looking at it at a sufficiently long distance. Okay, so clearly there is this radius, okay, and from the center, like I can now angle like this, right? Imagine this now instead of a slit, I have a circle here. So here I have a bigger circle, and then another circle starting. This will be the top and then the bottom of the next circle, and then the next one would be another circle. So you can see, you can imagine concentric circles being here. Okay, that's what I'm going to see. Okay, so this is how it's going to be. So in that case, what would be the angle? This theta. Now imagine it's a circle. So you take this circle and then consider this circle. Now it's not a slit, it's a circle now. It's an aperture, it's a circular aperture now. It's a circle like that. Okay. So if it is like that, then I can still find this theta, right? It gets flaring out. Light which is coming out of this will flare up and then make circles there. That's what is done here. So this theta is now given by this expression. Theta is equal to 1.22 lambda by d. Now d is the diameter no. Okay, check this parent, not good. Diameter of the circle. The circular aperture. That's what you get. Okay. So theta is 1.22 lambda by d. But here theta is 1 into lambda by a. A is the width of the slit. Here it is 1.22 lambda into the diameter of the slit. So the ratio is based on 1.22. It's easy for you to remember this. The proof of this, the derivation of this is not needed for you. It's beyond your scope, it's not even mentioned in your book, so we're not getting into that. But just remember that this angle theta is going to make, if it is a circle and if it makes a circle, then you can find the theta, right? The angle of this flare. This theta is now given by this expression, theta is equal to 1.22 lambda by d. Okay, we want to understand this. If it's a slit, it is just lambda by a. Because it's a circular aperture, it is 1.22 lambda by a, in this case is d. Right? Same thing, a and d are the slit width and the diameter respectively. Pretty much the same. So this has a profound impact basically. So what happens is, suppose, follow me closely. Here, let's suppose I have this one. This is going to be, I call this as A, and then I call this point as B, call this point as C, and call this point as D. Meaning that I will have that point A here, and then B somewhere here, and then C here, and then D here. Okay? But notice this. This A now must occupy a bigger area. Because you got only ABCD here, you have ABCD here. So this, all these things were occupying this space before, now they are occupying this space. But notice one more thing. If A is flaring up like this, then B will also be flaring up like this, right? Something like that. Okay, now you see it's getting into A. Then C will also flare up like this. And then D will also flare up like this. Okay. We'll get into C and then this one. So what I want you to understand that each point here is now not a point on the image, but a circle of certain width. In the ray optics, what did you have? If you have an object, here, and then the ray that is starting from the object, then it hit there. So it was a point, then it was a point here. It was a point, it was a point here. Point, it's a point here. Now that is not the case. What this point here now becomes a circle. So if it was a point here, then it becomes a circle there. And the next point, if I take, do something like this. You see there is an overlap. If they are all points, there is no overlap. Point to point. So next point to next point. Because point by definition does not have any dimension. But when a point gets converted into a circle because of this flaring out, you start as a point and then you go and then you flare out. Now you see the point now becomes a circle. You start as a point and then as you flare out, then it becomes a circle. Then you take the next point, then that will flare out and that will form the next circle. If the spacing between these two circles is not sufficient, so that one point has become one circle, another point has become the circle. Now you can see them as two different images. But suppose you are taking a point which is very close to the first point, then this circle will overlap with this like this. Now you see the image is going to get blurred. Now you don't see two different things, you see one smudge there. So the clarity is going to be affected by you. Then how can you increase the clarity? Yeah, simply by reducing this circle, right? The point, if it becomes instead of becoming a big circle, it becomes a very small circle. You see, then they're fairly well separated. And maybe I'll be able to accommodate one more point between these two without much of an issue. Okay, so now I'll be able to see three points where I was having difficulty seeing two. So if the circles become bigger, smaller and smaller and smaller, then I'll be able to see more points clearly. Okay, so I wanted to understand this. So if this is to happen, then if this conversion, the point getting converted into a circle, if this radius were to go down, then theta has to be small. So the flaring is smaller. The flaring is minimum. So if that has to happen, then either lambda has to be small or d has to be big. So this aperture, this has to be big, or you decrease the lambda. If you decrease the lambda, then the theta will be small. If the theta is small, then the flare up will be small. Won't flare up very much. It will be small. If that is small, then it will make each point here will become small circles on the screen when the light falls on the screen. Then you will be able to see more points. That's it. So you'll be able to see more points on the object if the aperture is big. Okay, I want you to understand this. In ray optics, remember this, in ray optics, each point on the object corresponded to each point on the image. But in wave optics, what happens is each point here corresponds to not a point but a small circle because of the diffraction effect. Because of diffraction, light flares up, it becomes wider. So a point here becomes a circle here. So when you have circles for points, then points can overlap on the other side. Here there is no overlapping. On the object side there is no overlapping. You have one point, another point, another point, another point, clear demarcations, clear difference, like among points. But here, one point can form this circle, the next point can form a circle like this, very close. Now you get a smudged value, like you don't see two different circles, two clear circles, but then you find a smudge and everything. They overlap. So you can't see the image very clearly. The points, like the details of the image very clearly. But if it is separated well enough, then yeah, it may be a circle, but you see, you will still be able to see the 2 points clearly. So the smaller the circle, the greater the points you'll be able to see clearly. Okay? Suppose if this makes a big circle, okay, and you see, let's say it's like this. It's like this. You see, there's an overlap. All these different points, you see now, there's an overlap. Here, they're well separated, but here, you'll see something like this. That's what you'll see. It's not very clear. But if I reduce the circle, If this becomes a smaller circle here, I'll be able to see the object very clearly. So for this to happen, theta has to be small. Why should theta be small? The flare-up has to be small. How can we make the flare-up small? Either by reducing the lambda, by sending a light of a different lambda, or by increasing the slit. If you increase the slit width, then you will be able to see things more clearly. Okay? So this is called as resolution. The resolution of a telescope and then the microscope have been omitted from the textbook now, so I'm not going to get into it now. But I wanted to give you this idea. So now you will be able to see these points clearly. You are able to see these points. You are able to resolve these points here, the image. So this is called as resolution. This you cannot resolve, but this is a clear resolution. This is a better way of looking at it. If it is really small, maybe like I will be able to see another point here between these two can also be seen here. Okay? Another point here. You see, I will be able to see more of them without botched by a diffraction effect. Okay, so it has now 1, 2, 3, 4, 5, 7. I'm able to see all the 7 here too. Even though they are not exactly points, they are circles, but very small circles. So that then I'll be able to see the light very clearly. So this is called as resolution. And you can calculate it for a telescope and also for a microscope. Okay? Even our eyes have the same issue, because the light that comes from outside has to fall on the pupil, and it has a certain diameter, right? So light has to fall on the pupil and to go through the pupil and converge on the other side. So even we have diffraction in the eye. Okay, so it is our eyes are not perfect. So because they are lenses and they are small opening, they are apertures, then this might happen with them. That is why you are able to see something big clearly. But then I will be able to see whiteboard without an issue. But then I will not be able to identify each and every point on the letters, like dimensions. There is a small size, beyond which I cannot differentiate those things. Okay. So you have our eyes are affected by diffraction effect, and any lens is affected by diffraction effect. That is why it is saying. Even when you talk about telescopes, you see this. Suppose I have a telescope or a lens. I just take a lens now and remove this. And take just a lens. Okay? The light will come here, and then this is like the aperture, right? The lens is like this aperture, and on the other side it's going to form images, right? So suppose if I take this point, or rather if I take one point here, then that would become a circle. A point on the other this side would become a circle here, right? So let's say this is a point here, and that will become a circle there. Okay. So how do you control this? How do you control this? This will be my theta. Right? This is my theta. So the total will be 2 theta. So this will be theta again. So 2 theta. So the total of this angle is 2 theta. But you know this, theta is 1.22 lambda by d. So theta is 1.22 lambda by d. And d, what's this? Okay. So if you want to make it small, then I should have a larger lens. The larger the lens, then the smaller the circle becomes for every point. And then this point will become a smaller circle here. Maybe this point will become a smaller circle there. Okay? And then I'll be able to see this point, sit here, this point, will sit here. And if I take this point, yeah, this is where I'm going to get a little bit of trouble. You see, now it is getting, we take this point, maybe like this. You see, it's getting much. But then if you take a point between these two, and you notice, then that has to overlap. So this detail I can't see. Because you see, this distance, as you reduce the distance between points, if you take a very, very, very close point, then you see that is getting disturbed there. So that is the reason we are not able to see many details. The diffraction effect will always happen in our eyes. Any lens, any opening, because light bends. And the greater the lens, then the greater the resolution will be, because the smaller the circle for each point on the object. Okay? So that is why you have big lenses. The objective piece, if you take, for example, if you take a telescope, you have a big lens, objective lens, and then a small lens here. Okay? So it's like this, right? Telescope is like this. The telescope is like this, objective, this eyepiece. Why? Same thing. Because the bigger it is, then the less the diffraction effect will be. So you will be able to see things, you will be able to see more details. But if I use a smaller lens with the same focal length, for example, if I use a smaller lens, okay, now you see this lens and this lens, both of them have the same focal length. They will have the same magnification. It doesn't depend on the sides, right? What is magnification? The magnification for a telescope is FO by FE. It doesn't talk about the size of the lens. So whether I have a small lens here or a big lens here, my magnification will be the same. But what is the problem? The problem is, when I have a small lens here, then each point of light I receive will become a bigger circle here. So I won't be able to see things all that clearly. So if you want to see a lot of details on the object, then I need to have a big objective. That's important. So that is the reason you can see that the telescopes with bigger objectives will give you images with a lot more details. We want to see the craters on the moon. With the telescope that I have, I will be able to have, I'll be able to see some details. But if my objective lens becomes bigger, then I'll be able to see more details on the moon. Maybe I'll be able to see craters within craters there. Okay? And so all the big telescopes will have, all the scientific telescopes that people use for research and stuff to study cosmology, they have big lens. You may ask, well, only the focal length is important. Magnification is F naught by Fe. So only the focal length is important. So why not have a small lens with the same focal length? After all, you know this, right? You know, like if you have, it's like spherical lens. I can cut it like this, or I can cut it like this. Why should I go for this? Both of them will have the same focal length, because this is going to be R. So focal length is going to be R by F is equal to R by 2 for this lens and also for this big lens. then why should I go for a big lens? That takes investment, right? Takes a lot more material. Okay, now why should I go for it? The reason I go for it is because if it is small, then diffraction effects will not give me the necessary detail. But the bigger the lens is, this will kick in 1.2 to lambda by d. Now d is more, so theta is small, the flare up is smaller. Because the flare up is smaller, each point on the object will make a smaller circle on the image. So I'll be able to see more points on the object clearly in the image. Okay, so that is the reason. I want you to understand this. If you have high resolution, then you will be able to see more details. If you have low resolution, then you won't be able to see as much detail as you were able to see before. Okay, and that depends on the size, one factor, and also depends on the lambda. But for visual things, the lambdas are fixed. Okay, but when you use electron microscopes and stuff, we'll get to know about it a little later. Okay, like that's what you use in the electron microscope. You use the wave nature of electrons. So the electron wavelength is very small. Ordinary light wavelength is not like that, right? It's 4,000 to 7,000 angstrom units. That's the wavelength you get. But the electron wavelength will be much smaller than this. And that is why when you use electron microscopes, you are able to see much more detail of an object. Why? Because light restricts you. There is a certain limit to resolution in the case of visible light because of the visible light wavelength range. But when you use an electron microscope, its wavelength is even smaller. So for the same aperture, for the same d, if lambda is small, then theta will be small. So if theta is small, the circle it makes will also be small. The point makes will be small. So you'll be able to see more and more points clearly in the image. So that is advantage. That's why you're using electron microscope. I hope you are able to connect what you studied in that lesson with this. Why do you have an electron microscope? Why can you not use light itself? Well, electronic wavelength is much smaller. Because the electronic wavelength is much smaller, the diffraction effect will be smaller for electron. Okay? Because the diffraction effect is smaller, you will be able to see much more detail in a picture which is created out of the electron microscope. So that's the reason. I hope you understand this. Okay, the next thing that we need to talk about is the validity of ray optics. You just write it down. The validity of ray optics. Why suddenly I talk about it? If light is a wave, we should be using wave optics all the time. Then why are we even bothered about ray optics? Why did we even study that lesson first? Because it is simple and it is also fairly accurate, it is working. So the question is, when will you start using ray optics and when will you stop using it? So what is the validity of ray optics? Clearly, light is a wave. Okay? So even if you take small distances and all this stuff, small distances, the wave nature should hold good. But sometimes for small distances, the wave nature, the effects of the wave nature of light is not felt that strongly. So you can, you can treat light as rays for small distances. And how small is the distance? But what am I talking about? Why do I even say that? With small distances, the ray optics effect the wave optics, the wave nature of light is not felt. Let me take a case and illustrate that to you. For example, let me take the single slit experiment itself. So I have this slit here, and then light is coming out. Okay, but what happens is that it is spreading out, and this is what's happening. Where you should have seen only the bright spot here, you are seeing the bright spot for a longer distance area. But if I take this point, then clearly this will also flare out, right? Flare out like this. And if I take this point, see, this will also flare out, right? If I take this point, see, this will flare out like that. Take this point, flare out like that. You see, if I bring it closer and closer and closer, you see there will be some distance. Look, this has become this, separate. Whereas I take it, move it away, if I go further, then they start interfering. It becomes the interference, the diffraction effect becomes more, it becomes dominant there. From here, if we bring it here, and just draw two, okay, it's like this. One point, and there is another point, it's like this. So if I keep the wall here, you see this light from one point is meddling with the light from the other point. And if I come here, then it still happens, but then it is happening for small distance. But then if I come here, if you notice, then this is the light from that point, this is the light from this point, from the slit. So as you come closer, then the interference, the diffraction effect doesn't, the wave nature of light is not that predominant. But as you go away, move away, then this will be predominant. So what is the distance? What is the distance over which you can use the ray optics? That distance is called as Fresnel's distance. It is named after a French engineer, Augustin Fresnel. That guy lived for only about 39 years. Okay, he didn't even live long. When he died, he was just 39, less than 40. Passed away. He was a brilliant engineer, a French engineer, Augustin Fresnel. So you call something as the Fresnel distance. So Fresnel distance is the distance at which the wave nature, the wave effect of light is taking over the ray nature of light. Okay? Let me put it that way. From that point, like you have a source point, and then you have a destination point, and then you may measure some distance. If it is Fresnel distance, beyond that point, then interference and diffraction and all the other effects will be predominant. So you have to treat light as wave beyond that point. Between this point, like the Fresnel distance and the Fresnel point and the source point, within that distance, the Fresnel distance, you can treat it as, treat light as a ray. You can still treat that as a wave, but then it's an overkill. Okay, you don't have to, because like treating light as a wave involves a lot of mathematics, So within the Fresnel distance, you can treat light as a ray. Beyond the Fresnel distance, you cannot treat it as a ray because the wave effects will be felt, will be predominant beyond that distance. So what is that distance? That is called as a Fresnel distance. And within that, you are justified in using these diagrams. Okay, these diagrams. This is the object, A, B, and then you get right here, and this is the A dash, and this will be dash, all that. But this happens. This can be used only within the Fresnel distance. Keep that in mind. Then how do you calculate that? Okay, so to calculate it, you do it like this. Well, I have a slit. Okay, and light travels through the slit, basically. Then there is a screen, and then you know, and there is this theta, right? Okay, and this is E. So what do you know? Theta is equal to lambda by A for the maximum. This is the minimum, so that is a condition, right? So this is where the maximum ends. So that is the theta you are taking. Theta is equal to lambda by A. Okay. So as this flares out, this flaring, take this flaring. And suppose this is a distance C. Okay. And this is theta. So if Z is long enough, then this distance and this distance will be the same. This will be Z, this will be Z, because Z is a long distance. Okay. In that case, what is this width? This width, I will call it as X. X is given by Z theta. What is this distance? Fresnel distance is the distance Z at which this X is equal to A. So Fresnel distance ZF is the distance, from the source to destination. Okay, where X becomes A. If this width is equal to this width, the slit width, then beyond this distance, the interference effects will, the diffraction effects will dominate. Beyond this distance, once X has become A, you cannot use ray optics for this distance. You will be in trouble. But within this distance, you can use this. You can use ray optics. Okay? So, what do you get now? So, Z is ZF, right? Okay, when X is equal to A, then A is equal to ZF to theta. So theta is equal to A by ZF. So what do you know? You also know that theta is equal to lambda by A. So this is 1 and this is 2. So 1 is equal to 2. So that gives you A by this Fresnel distance ZF is equal to lambda by A. And this gives you ZF is equal to A squared by lambda. So I want you to understand this. So Fresnel distance is the distance beyond which the wave nature of light dominates. Within the Fresnel distance, you can use ray optics. So ray optics, the validity of ray optics is within when D or when Z, I should say, when Z is less than ZF. When Z is less than ZF. Ray optics is valid. Within this distance, ray optics is valid. Beyond that distance, ray optics is not valid. Okay. So we'll do a small problem to illustrate this. Okay, we'll do example problem 10.7. This is a problem. For what distance ray optics is a good approximation if the aperture is 3 mm and wavelength is 500 nanometers. Okay. So what is that? So if you have an aperture, so this is the aperture, and this width is 3 millimeters, and then the lights that you use, right? This has a lambda of 500 nanometers, and clearly, or you're going to have a screen somewhere, then this will flare out. Okay. I should have only this. Now it is flaring out, right? So this is the distance Z. But till what distance can you use? You can use only till ZF, right? The Fresnel distance. The Fresnel distance is given by the expression A squared by lambda. What's your A? That is 3 millimeter, which is 3 to 10 power minus 3, the whole square, divided by what is this? 500 nanometers. So 500 to 10 power minus 9, so we can 5 10 power minus 7, so you get 9 into 10 power minus 6 divided by, this would be 5 into 10 power minus 7. So 1 minus 1, so it will go up, so 9 by 5 is 1.8 into 10 power minus 1, so that is equal to 18 meters. So if you have a 3 millimeter aperture, it's a very small aperture, for 3 millimeter aperture, I can use ray optics for 18 meters. So that's about 60 feet. So even if I have a small aperture like this, 3 millimeter aperture, ray optics is good till roughly 60 feet or 18 meters. You see, you can, for all common situations, you can use ray optics, because what kind of experiments would you do beyond 60 feet or something, even for a very small aperture? But let's take this lens. Okay, this is the kind of lens that you would be doing your experiments with, the ray optics experiments, right? But actually light is away, but you will be doing your experiments with this lens, and by drawing arrows, treating light as a ray. Are you justified? You are definitely justified, because for 3 millimeter itself, you can use ray optics for 18 meters. So let's calculate how long we can use ray optics for this lens. I just measured it. This size is about 5 centimeters. Okay. So 4.5 for all practical purposes, just take it as 5 centimeters. It will make my calculation easier. So that's the width of this lens. Okay. So I have this lens here, and then light will come, and then I'll have a screen there. See, then I'll have Z here for this aperture. Okay. So ZF again is equal to A squared by lambda. So I told you A in this case is 5 centimeters roughly, actually 4.5, we'll take it as 5. So that is going to be equal to 5 into 10 power minus 2 square. I will use the same average, 5 into 10 power minus 9 nanometers. So this gives me 25 into 10 power minus 4, so divided by 5 into 10 power minus 7. Okay, so this is 5 and this is 3. So equal to roughly 5,000 meters. So for 5 kilometers from here, we take this lens, if we keep this lens here, for 5 kilometers on this side and this side, I can use ray optics. So only after 5 kilometers you can feel the wave nature, the diffraction effects and the interference effects, all that will become predominant only after 5 kilometers from this. But till then, within 5 kilometers, you can treat light as a bunch of rays. You are justified in treating light as a ray for 5 kilometers for this lens. Well, if you have a bigger lens, then you can treat it for even longer distance. You will be justified. So it depends on the size of the aperture, as we saw. Okay. Okay. Even if you take our own eye, for example, the size of the pupil is roughly about 1 millimeter or even 2 millimeters. If you take, let's say like 2 millimeters. If I do that, even if you take 1 millimeter, let's say, if my eye, the pupil in the eye, right? So I'll just say the pupil in the eye. Even if I take it to be 1, okay, we take this to be 1 millimeter, then if I do calculate the Fresnel distance of the pupil, then we'll get a squared by lambda. So I'm going to get 1 into 10 power minus 3 the whole square, so divided by the same 500 or 600, 10 power minus 9. So that will be 1 into 10 power minus 6 divided by 5 into 10 power minus 7. Okay, that's going to give me 10 by 5. Yeah, 2 meters. So even if I use my pupil for 2 meters, okay, 200 centimeters. For 200 centimeters, I can treat light as a ray. But what is the size of the eyeball? I told you. It's like this, right? I said when we are doing this problem, it's 2.5 centimeters roughly. So this is my eye, this is eyeball. I have the retina here. Inside, okay, it's just 2.5. But I can treat light for this size of the pupil, for 1 millimeter size of the pupil. I can treat light as a ray for how long? For 2 meters. And I have only 2.5 centimeters. So I am justified in using ray optics for all things involving the eye, for almost all things involving the eye. Sometimes you will see floaters, okay, but that's because of the diffraction. Let's decide the point. Okay. So for all images that I see with my eyes, I am justified in using ray optics, even though I know that light is a wave. Because even for this size, for 2 meters, I will not feel any wave effects. They are not that pronounced. They are negligible. The diffraction effect of light is negligible for at least 2 meters. And I am very, very safe. I have got only, instead of, when I can use ray optics for 200 centimeters, 2 meters, 200 centimeters, my eye has a distance of only 2.5 centimeter, So nothing, practically nothing of wave nature will affect my eyes. I'm justified in doing it. Okay, so hope you understand this.